Okay, so hi everybody, welcome back. Today we're going to be starting a new lecture on optical instruments, and the material in this lecture is mostly coming from chapter 33 of the textbook, but also a little bit from chapter 32, specifically section 3 of chapter 32. So let's get into it. So the main goal of this lecture is for us to gain a basic understanding of how optical instruments work. So we're talking about things like mirrors and lenses. We want to know, how do they focus light and how do they form images? So at first, we're going to start simple. We're going to just look at a single mirror or a single lens. But then later on, we'll build up to more complex situations where you have multiple mirrors or multiple lenses in some kind of combination. And when you have that, you can make, let's say, a microscope or a telescope with multiple mirrors and multiple lenses. But the basic principle, the basic physical principle behind most optical instruments is really simple, and it's something we've seen before. So I'm talking about the law of reflection and the law of refraction, better known as Snell's law. So remember, if you have a ray of light coming in and then reflecting off of a surface, the law of reflection says that the angle of incidence is equal to the angle of reflection. And of course, these two angles are measured relative to the normal line of the surface. So that's basically how reflection works. On the other hand, Snell's law says that if we have a ray of light which moves from one material into another material, that ray is going to be bent. And we can see exactly how it bends by measuring two different angles. So this is the interface between the two surfaces. This is the normal line to that interface. And so we measure the angle of the incoming ray as theta 1 relative to that normal line. And the outgoing ray, theta 2, also measured relative to that normal line. And Snell's law says n1 times sine theta 1 equals n2 times sine theta 2. So all of the basics as far as how optical instruments work can be understood just using these two physical principles. So this lecture is going to be all about applications of these principles. Okay, so a really important concept to understand right off the bat is how mirrors and lenses form images. Okay, so what does it even mean to say that an image is being formed by a mirror or by a lens? So let's discuss that. So let's say we have some sort of object, maybe this chair here. And in general, every single point on the surface of that object is going to be a source of light rays. And those light rays travel outwards in all directions. So here, I'm going to just select this point at the very top of the chair. What I'm saying is there's going to be light rays emitted in all directions from that point on the chair. Now, why is that? Well, it could be a few different reasons. The object might be emitting its own light. So your object could be a candle or a light bulb, something that's emitting its own light, or it could just be reflecting other light. So pause to think about this for a second. If you just look at the room around you, okay, if you can see a chair, if you can see a water bottle sitting on the table, those things are not emitting their own visible light. Those things are just reflecting light from either your lights in the room or sunlight coming in through your windows, and that reflected light is going into your eyes. That's why you see it, okay? So for the most part, objects you just normally see around you are diffusely reflecting other light, and that's how you can see them. Okay, so now let's say we put a lens next to that object. Well, if we follow some of those outgoing light rays from that point, the lens can actually bend those light rays so that they're coming together. Okay, so they were diverging before, but now they're coming back together. And there's some point where those outgoing light rays actually meet again. Okay, and that's where an image forms. So an image forms when the light rays emitted from a single point on the object, which would be over here, come back together, they converge at another point, okay? And just to be clear, we're only keeping track in this picture of the rays emitted from the top of the chair, so those converge here, but we could play the same exact game with any other point on the chair, and we'd see that, well, these rays converge over here, these rays converge over here, and that forms an overall image of the chair. Okay, so the lens is forming an image of the chair. That's what's going on. Okay, and with that introduction out of the way, let's talk about thin lenses. So a lens is just a curved piece of glass or some other type of transparent material that we can use to either concentrate light, meaning converge light rays, bring them closer together, or disperse light, which is to make light rays diverge, make them go further apart. Now, we're only going to concern ourselves in this lecture with thin lenses because the math is a little bit more simple when we use what's called the thin lens approximation. And so a thin lens is made of curved surfaces that are much smaller in diameter than the radius of curvature. So let's try to understand what this means. So let's look at this picture here. This is going to be our lens. And as you can see, the lens is made out of a curved surface and another curved surface, which are kind of slapped together. And by the way, we're looking at the lens from the side here. Okay, this is the side view. If we were looking at it face on, it would look circular like this, right? But looking at the side profile, this is what we see, the two curved surfaces. So this is obviously not a complete circle, right? It's just a small section of a circle, but if we draw that circle that lens surface is a part of, it has a certain radius. So there's a radius of curvature to that lens surface. Let's call that R. And then, of course, the diameter of the lens is D. So what we're saying here is D is a lot smaller than R. That's basically the thin lens approximation. So because we can form a lens by basically putting different curved surfaces together, there are different types of lenses we can deal with. So in particular, I want us to understand two types of lenses. We have what's called a double convex lens here, where we have two convex surfaces forming the lens. This is what it looks like from the side. And this is a double concave lens. It's made of two concave surfaces that are joined together. And again, this is what it would look like from the side. So we're going to mostly be focusing on these two types of lenses, double convex and double concave. Okay, so let's take a look at what Snell's law tells us about the way light travels in a lens. Okay, so Snell's law says n1 sine theta 1 equals n2 sine theta 2. So the idea is we have some kind of interface between two materials. N1 is up here, N2 is down here. This is the normal line. And so the incoming ray comes in at an angle which we'll call theta 1. So what can we say about theta 2 in different scenarios? Well, let's say we're going from air into glass. Okay, so the air, which would be N1, has an index of refraction that's smaller than glass, which is N2. So in other words, we have N2 greater than N1. Okay, well, if we look at Snell's law, and we have N2 greater than N1, that means theta 2 is going to have to be less than theta 1. Okay, so in this case, if theta 2 is less than theta 1, what's happening is the ray is bending towards the normal line. Okay? But what if we look at the opposite case, which is going from glass into air? So in this case, N2, which is the index of refraction of air, is going to be less than N1, which is the index of refraction of glass. And that will imply, using Snell's law, that theta 2 is greater than theta 1. In other words, the ray that comes out of the glass going into the air is bending away from the normal line. Okay? So the takeaway point is, if you're going from low to high N, what you get is a ray bending towards the normal line. If you're going from high to low N, then what you get is a ray bending away from the normal line. Okay? So just keep that in mind for what comes next. And so now we can understand refraction in a thin lens. In other words, how do light rays bend after they go through a thin lens? So we'll take a look at two different cases, the double convex and the double concave lens. And what we want to understand here is, let's say we have parallel rays coming into the lens. How do those rays travel after they exit the lens? Okay, so if we use the double convex lens as our example, let's take this ray right here, which is actually hitting the lens surface at an angle of 0 degrees relative to the normal line. Well, in this case, the ray that goes into the glass is not going to be bent at all. It's also going to be at 0 degrees. And then as we approach this lens surface, this will also be at 0 degrees relative to the normal line. So it will exit at that same angle. So only in this case, if you hit the lens surface at an angle of incidence of 0 degrees, it will just go straight through the lens with no bending. On the other hand, any other ray is going to hit at an angle that's not exactly 0 degrees. So let's take this one, for example. This ray comes in, and notice we're going from low N to high N, going from air into glass. So that means the ray that goes into the glass is going to be bent towards the normal line. Okay, so that's what we're seeing here, is this ray is bending towards the normal line. In other words, this angle here is smaller than this angle. Then next, we go through the lens and we encounter this second interface, this second surface. And now, as we go from the glass into the air, now we're going from high N to low N, which means the ray is going to bend away from the normal line. So this is our normal line to this surface, which means this angle of the outgoing ray is larger than this angle of the incoming ray. And so we're bending away from the normal line like so. So notice what's happening. These rays that were parallel before are now coming together. In other words, they're converging. That means a double convex lens is an example of a converging lens because it takes rays that are parallel and it makes them converge. It makes them come together after they exit the lens. So on the other hand, if we take a look at the double concave lens, again, if we have a ray that hits this lens surface at an angle of 0 degrees, it's not going to be bent, so it's going to go straight through like this with no bending. If we take a look at any other ray, let's say this one over here, then we can understand how it's going to be bent after going through this surface. So this is the normal line. Again, we're going from air into glass, which is low N to high N. So this ray should bend towards the normal line. So that's what we're seeing here. Then that ray goes through the glass. and then we encounter this lens surface. And so now we're going from glass into air. So we're going from high N to low N, which means the outgoing ray is going to bend away from the normal line. But when that happens, you'll see that this ray is actually not going to converge with this ray. In other words, the rays that are exiting the lens are diverging. Okay, they're going further apart from one another. So this is what we call a diverging lens. The rays that come in parallel will diverge after exiting the lens. And so that takes us to the idea of a focal point of a lens. So the focal point of a lens on a diagram is typically going to be labeled with a capital F. And this is a point where incoming parallel rays will converge after they go through a lens. So let's take a look at this case here. We have a double convex lens or a converging lens. And we have a bunch of rays coming into the lens. They're all parallel to one another. And we know that after they go through the lens, they're going to be refracted. They're going to be bent. In this case, they're going to be bent in such a way that they come together. That's what a converging lens does to a bunch of parallel rays. So these rays that exit the lens are coming together, and if we follow those rays, we'll see that they converge at a certain point. So that would be the focal point of the lens, where those rays come together. Now, if we take the case of the double concave lens over here, which is a diverging lens, well, if we have a bunch of rays coming into that lens, which are parallel to one another, they don't actually converge after exiting the lens, right? They actually diverge further apart after exiting the lens. So no matter how far I trace these outgoing rays, I'll never see them come together. But if I take those outgoing rays and then I trace them backwards behind the lens, so that's what this dashed line represents. It's the outgoing ray if we trace it back behind the lens. Then we'll see that those actually converge. So these dashed lines are what we call virtual rays. They're not actual rays of light. They're just what we would get if we trace the outgoing rays back behind the lens. So those virtual rays do actually converge at a certain point. And again, the idea is there's a focal point for the diverging lens. Okay, so there are a few other things to note about diagrams of lenses. The first is the optical axis. So the optical axis is a line that goes through the center of the lens and is perpendicular to both faces of the lens. So in this case, the optical axis would be this dashed horizontal line right here, because again, it goes right through the center of the lens like this, and it's perpendicular to both faces of the lens, as you can see here. So that's something we'll commonly label on diagrams, the optical axis. Okay, the other thing is something called the focal plane. So, of course, if we think about these parallel rays coming into the lens, they'll focus right here at this point. But what if these rays came in at a different angle? So right now they're actually parallel to the optical axis, but what if instead these parallel rays came in at an angle relative to the optical axis? Well, then they would focus somewhere else. They might focus up here or down here. And in general, the focal plane is where all of those different focal points of the lens will lie, okay? That's what we call the focal plane of the lens. So to clarify this idea of the focal plane a little bit, let's draw a couple different diagrams. Here we have a converging lens, and this would be the optical axis. So this line goes through the center of the lens, and it's perpendicular to the lens surfaces. So what we saw is if we have these parallel rays coming in, and in this case they're parallel to the optical axis, we know they're going to converge after going through the lens at a focal point, which is right on the optical axis. But the rays don't have to come in at that angle, okay? We can look at another case where those incoming parallel rays are maybe going at this angle. So they're not exactly parallel to the optical axis. Well, in that case, the rays would focus over here somewhere, just below the optical axis. And so this would be our focal point. Okay, so there's not just one focal point. There's a whole plane where all the different focal points lie, and that's what we call the focal plane. So you'll focus the light at different points along the focal plane depending on what angle those incoming rays are coming in at. And so related to that is something called the focal length of the lens. So focal length, typically denoted by lowercase f, is a distance. It's the distance along the optical axis between the focal point and the center of the lens. So it's just how far away from the lens is the focal point. Okay? That's what the focal length is telling you. And there's a way of calculating the focal length, and we use something called the lens maker's equation to do this. I'm not going to derive this equation for you. There's a derivation given in the book. Let's just take a look at the result. Okay, this says 1 over f, that's 1 over the focal length, is equal to n minus 1, where n is the index of refraction of the lens material. Again, typically this is going to be glass. And then we have 1 over r1 plus 1 over r2. So r1 and r2 are the radius of curvature of each lens surface. So let's say we have a double convex lens like this, okay? So we have a lens surface here, and then we have another lens surface here. This is what it looks like again when we see the lens from the side. So the first lens surface has a certain radius of curvature. Again, if we consider the surface to be a section of a circle, we can draw the entire circle and then state what the radius of that circle is. That would be R1, the radius of curvature of that lens surface. And then R2 would be the radius of curvature of the other lens surface. That's what R1 and R2 in this equation represent. And the same thing would be true if we had a concave lens. Again, we have a concave surface here, another concave surface here. Each one of those has a radius of curvature. Okay? Now, there's a sign convention for this equation that you have to be aware of. We consider the radius of curvature to be positive for convex surfaces. So these two R values, R1 and R2, would be positive for the convex surfaces, but they would be negative for concave surfaces. So these values of R1 and R2 would be negative for the concave surfaces. Okay, so let's do an example. We have rays of sunlight going through a converging lens, which is made out of glass. N is equal to 1.53 for this glass material. The rays focus at a point which is 25.0 centimeters in front of the lens. And the lens is made out of two identical convex surfaces. So the question is, what is the radius of curvature of each lens surface? Again, we have a bunch of parallel rays coming into the lens. After these parallel rays go through the lens, they converge and they focus at a point which is 25 centimeters away from the lens. So given that, try to figure out the radius of curvature R for each lens surface. So pause the video, see if you can work this out, and then we'll go through it together. Okay, so we'll start with the lens maker's equation. And this states that 1 over f is equal to n minus 1 times 1 over r1 plus 1 over r2. And what do we know? We know that f, the focal length of the lens, is equal to 25 centimeters to start off. Well, the reason we know this is that, again, we have these parallel rays coming into the lens, and then after they exit the lens, they all converge 25 centimeters away. So that would be the focal length. And the index of refraction is also something we know. That's 1.53. That would be the index of refraction for glass. We also know that the two lens surfaces are identical, meaning they should have the same radius of curvature. R1 should be the same as R2. Let's just call that R. Okay, so we have 1 over F equals n minus 1 times 1 over R plus 1 over R, because again, these are the same thing. So that gives us 1 over F is equal to n minus 1. We can combine these to say 2 over R. And our job is to figure out R. So if we solve for that, R equals 2 times n minus 1 times F. So that gives us 2 times 1.53 minus 1 times 25 centimeters, which equals 26.5 centimeters if you crunch those numbers. So the radius of curvature of both of the lens surfaces is 26.5 centimeters. So that brings us to ray diagrams. So a ray diagram is a very useful tool, and we're going to be using this throughout the chapter, which helps you visualize how an optical instrument can form an image. So we can use this for lenses, we can use this for mirrors. For now, let's consider a converging lens. Okay, so the idea is this. We have an object. So typically we'll show the object as an upright arrow. And then we have a lens. This is the optical axis. And then F marks the focal point of the lens. So we actually have a focal point here and here on either side of the lens. So we'll label this as F and we'll label this as F prime. Okay, the idea is we're going to take the object and specifically the top of the arrow, the tip of the arrow, and we're going to see how a ray, which goes from the tip of the arrow through the lens, travels after going through the lens. And then we'll do it again for a different ray, and then we'll do it a third time for another ray. So these three rays, which start from the object and then go through the lens, are called the three principal rays. So if we can find the point where those three principal rays converge, where they come together after going through the lens, then we know where the image forms. Okay, that's the idea. So when we consider the rays of light being emitted by the object, specifically, let's think about rays of light emitted from the tip of the arrow. These will be traveling in all different directions, okay? So we're simply going to look at three of those rays. We're just going to focus on three of those rays emitted from the tip of the arrow, and those are called the principal rays. Now the first principal ray is going to be emitted from the tip of the arrow and then go parallel to the optical axis. And then after it goes through the lens, it's going to go out through the focal point of the lens. Remember, any ray that travels parallel to the optical axis is going to have to go out through the lens through the focal point. So we saw that earlier. The second principal ray is going to go like this. First, it goes through the focal point F prime on the other side of the lens. And then after that, after going through the lens, it's going to travel parallel to the optical axis. So the idea behind this second principal ray is basically the same as the first, right? If we travel parallel to the optical axis here, then we have to go through the focal point over here on the other side of the lens. Now the third principal ray goes exactly through the center of the lens without changing direction. Okay? And so if we look at these three principal rays, 1, 2, and 3, we see that they all converge, they all meet on the other side of the lens. So that's where the image forms. The image forms where these outgoing rays converge. Now remember, we were following the tip of the arrow, right? So this is our object. This is the tip of the arrow. Those rays converge down here, so this must be where the image of the tip of the arrow is forming. And actually what that's telling us is the image is upside down. It's inverted. So let's take a closer look at principal ray number 3. I think the other two are pretty straightforward, but ray number 3 deserves a closer look. So let's draw the lens like so. So we'll look at it way, way close up. And the idea behind this ray is that it goes straight through the center of the lens. Okay? So this is the ray that's entering the lens. Let's say it enters the lens at an angle theta 1. So after traveling into the lens material, which is glass typically, it's going to bend towards the normal line. So that's what I'm showing here. Theta 2, let's call this angle, is smaller than theta 1. And again, this goes right through the center of the lens. Okay, now, when we exit the lens and go back into the air over here, we're going to be going out at some angle. So let's call this angle theta 3, and let's call this angle theta 4. So what I want to convince you of is that the outgoing ray is moving in the same direction as the original incoming ray. So here, this is the incoming, and this is the outgoing ray. Okay, so remember, we're using what's called the thin lens approximation here, which means the radius of curvature of the lens surfaces is much bigger than the size of the lens itself. And so what that implies in our diagram is that the two normal lines that we drew are basically parallel to one another. It's not exactly true, but again, as long as these two lens surfaces have a very, very large radius of curvature, then the two normal lines I drew here and here will basically be parallel to one another. So, in other words, we can treat theta 2 and theta 3 on the diagram as alternate interior angles, which means they're the same. Theta 2 is equal to theta 3. But if theta 2 is equal to theta 3, that immediately implies that theta 1 is equal to theta 4. And that's what we were trying to show. The incoming ray and the outgoing ray are moving in the same direction, which is why we have principal ray number 3, which goes through the center of the lens without changing direction. That's where this comes from. Okay, so next, let's take a look at how we can make a ray diagram when we have a diverging lens. So here in the diagram, we have a diverging lens. It's a double concave lens. This is the optical axis as before. We have our two focal points along the optical axis. And here's the object. It's an arrow pointed upright. So again, the idea is we're going to take three principal rays, which originate at the tip of this arrow, and we're going to follow them as they go through the lens, and that will give us an idea of where the image is forming. So the first principal ray is parallel to the optical axis, just like before. And then it goes out through the lens. But remember, this is a diverging lens. It's not going to go out through this focal point here. It's going to diverge, go further away from the optical axis like this. But if you trace it back behind the lens, you'll see that it goes through this focal point, F prime. Okay, so that's our first principal ray. Next, our second principal ray goes towards this focal point, towards F on this side of the lens. But then after going through the lens, it goes out parallel to the optical axis like this. Okay, so principal ray number 2 goes towards this focal point on the opposite side of the lens, and then bends so that it's going parallel to the optical axis after going through the lens. And so we'll do a similar sort of thing with this outgoing ray. If we trace it back behind the lens, we'll see it's moving this way. And then finally, the third principal ray is just like before. It goes through the center of the lens without changing direction. So if we look at ray number 1, ray number 2, and ray number 3, these outgoing rays do not converge on the opposite side of the lens. Instead, what happens is if you trace those rays back behind the lens, you'll see they appear to converge back here. Now, this is a really important point. The actual outgoing rays, 1, 2, and 3, are not converging. They only appear to converge if you trace them back behind the lens. So here is where the image is forming. And since we were following from the tip of the arrow, we see the image forms here. This will be an upright image. In other words, it's not flipped like before. And this is what we call a virtual image because, again, there's not an actual convergence of rays happening there. It just appears to be that way if you trace the outgoing rays back behind the lens. So this is an example of a virtual image. So what we've just illustrated by looking at these two different ray diagrams is that there are different types of images that can form depending on the situation, depending on what type of lens you're using, and some other factors. And so first, let's talk about the difference between a real image and a virtual image. So a real image is formed when the outgoing rays, that is the rays that are coming out of the lens, converge on the opposite side of the lens as the object. So if you have rays actually converging after going through the lens, then you get a real image. On the other hand, a virtual image is formed when the rays coming out of the lens, the outgoing rays, diverge, but if you trace them back behind the lens, they appear to converge back there. So one really important difference between a real and a virtual image is that with a real image, you can project that image onto a screen or onto a wall or some surface because rays are actually converging there. You can't project a virtual image onto a screen because there aren't any actual rays converging when it comes to a virtual image. However, our eyes are capable of seeing both real and virtual images. Okay, now another difference is between upright and inverted images. So an upright image has the same orientation as the object, but an inverted image is flipped upside down about the optical axis. So again, we saw an example of both types of image in the two ray diagrams that we drew. And then lastly, you might have noticed in the ray diagrams we made that the object in the image don't always have the same size. So that brings us to the idea of lateral magnification. Lateral magnification is the ratio of the image height to the object height. So M is defined as HI over HO, where this is the height of the image and this is the height of the object. So let's think about this real quick. If your image is bigger than your object, then your magnification is going to be greater than 1. If your image is smaller than your object, then your magnification will be less than 1. And if they're the same exact size, then your magnification is equal to 1. So basically, magnification greater than 1 means you're getting a blown up image, something that's bigger than the original object. Okay, so next, I'd like to show you how a lens can form an image. So in this demonstration, we have a converging lens and a light source, which is just provided by my phone. So what I'm going to do is hold the lens next to the light source, let the light go through the lens, and then project that onto the board here. So notice if I hold the lens and the light source at just the right distance, I can get a sharp image of my light to actually project onto the board. So we have an image forming on the board right now. And what's happening is, after the light exits the light source of my phone, the rays spread out. But then after going through the converging lens, they converge, they go back together. The point where all of those outgoing rays converge after leaving the lens is the point where the image formed on the board. So since the outgoing rays leaving the lens actually converged somewhere, we call this a real image. So any real image can be projected onto a screen or onto a board like this. So on the other hand, if I have a diverging lens like this, then I can create what's called a virtual image. So I'm going to put the diverging lens right here and then just put my hand behind it. And you can see that there's an image formed of my hand by this lens. You can see that pretty clearly. And it looks like this image is being formed back here behind the lens. So if you think about it, the light rays going through the lens, after they exit the lens, they're not converging anywhere over here. In fact, they're diverging, right? So there's no point where the outgoing rays actually converge and form a real image. It's just that if you trace the outgoing rays back behind the lens, it appears like they're converging somewhere back here. That's where the virtual image forms. But again, this is not an image I could project onto a screen or anything because there aren't actually any rays converging at any point. And so I want to leave you a link to a really interesting web page, which is an online geometric optics simulator. So in this simulator, you can place different mirrors and lenses in a virtual environment along with different light sources, and you can see what happens to the light rays. So it basically automatically generates a ray diagram for you in any situation that you set up. So this is a really useful tool to play around with. You can use this to sort of help you with homework problems and to just get a better idea of what's going on in terms of the ray diagrams. So I'm not going to show you the web page here in this lecture. I'll just leave the link. Definitely check this out if you want to use the online geometric optics simulator. So with that said, here we're going to derive some very important equations that apply to thin lenses, okay? We're going to derive what's called the thin lens equation and an equation for lateral magnification. And so here's how we're going to do this. We're going to start with this diagram, which admittedly has a lot going on, so let's discuss. So here we have a lens, and for the purposes of this derivation, we'll take it to be a converging lens. And here we have our object. So this is the arrow pointing upright. So we're going to show two principal rays. One of them goes parallel to the optical axis out through the focus like this. The other is going straight through the center of the lens without being bent. Okay, the height of the object is HO. The height of the image, which is actually inverted in this case, is HI. The distance between the object and the lens is what we'll call DO. And then the distance between the image and the lens is what we'll call DI. And then, of course, F is the focal length. That's the distance between the focal point and your lens along the optical axis. So we have these different distances here. I've also labeled a whole bunch of points, which we'll refer to as we go through the derivation. So we have O and O prime, I prime, A, B, F, and F prime. These are just different points that we'll refer to as we do the derivation. Okay, so we'll start by noticing that in this diagram, we have two pairs of similar triangles. So the first one I'd like to point out is we have the triangle formed by the points O, O prime, and A. and then also the triangle formed by the points I prime, and A. Okay, so here's the first one, O prime A. And here's the second one, I prime, and A. So those are the two triangles I'm pointing out. And let's just copy them down on a separate area so we don't clutter the diagram up too much. So, okay, O prime A is this guy. And there's a right angle here. And let's call this angle up here beta, and let's call this angle over here alpha. How about? Okay. Now the other triangle that I pointed out was I prime A. So here's I prime, and A. And notice how this is also a right triangle. And here's the angle alpha in the diagram that I was referring to earlier. So it's the same angle alpha in this triangle as we had before. And this angle is also the same angle beta that we had before. So these are two similar triangles. They have the same exact proportions, in other words. One is just a scaled up version of the other. And so we can use that fact to relate the side lengths of the two triangles, because here, actually, before we do that, let's label the side lengths. The distance between O and O prime is HO, the height of the object. The distance between O and A is DO, that's the object distance. And then on the other triangle, the distance between A and I is DI, that's the image distance. And then the distance between I and I prime is HI, that's the height of the image, okay? So here's what we can do to relate the two triangles. Tangent of alpha. Of course, that's the opposite over the adjacent side, but it's the same angle on both triangles, so we can apply this to the first triangle, which gives us, okay, the opposite side to alpha is HO, the adjacent side is DO, using the first triangle. Using the second one, the opposite side is HI, and then the adjacent side is DI. So this gives us HI over HO equals DI over DO. So remember, HI over HO is what we call the lateral magnification. So apparently, the ratio of the image and the object height is also the same as the ratio of the image and the object distance, okay? So there's another set of similar triangles on this diagram that I want to point out. We have a triangle ABF, and we have another triangle, which is I prime F. Let me label those real quick. So here's ABF right there. And then here's I prime F right there. Those are the two triangles. So there's an angle that's shared by the two triangles, which I'll label right off the bat. Let's call this omega here. And it's the same omega down here. And again, let's draw the two triangles. We have ABF. So point B is up here, point A is down here. And then point F is over here. This is a right triangle. The angle omega is right here. And let's call this angle up here, I don't know, epsilon. Okay. Now, going from A to B, if you notice, that's the distance HO. That's the height of the object. Okay, so in other words, this distance right here from A to B is the same as HO. And then this distance from A to F is what we call the focal length. So this side length will be F, the focal length. Okay, our other triangle looks like this. We have I prime, and On this side, we have F. So this is another right triangle. Again, this angle omega is the same as in our other triangle, which means this is the same angle here, epsilon. So we have two similar triangles. Now, the distance here between I and I prime is hi. So that's this side length on the triangle. And then the distance between I and F, this distance is di minus F. So this is the image distance minus the focal length. Okay, so those are the two triangles. And just like before, we can say there's a tangent of an angle, let's call it tangent omega, which would be the opposite side over the adjacent side for both triangles. So using the first triangle, the opposite side is HO, and the adjacent side is F. But using the second triangle, the opposite side is HI, and the adjacent side is DI minus F. Okay, so if we rearrange that, we have HI over HO equaling DI minus F over F. But remember from earlier, we said, so using the previous result, we said that DI over DO is the same as HI over HO. So I can replace HI over HO with DI over DO. So DI over DO is DI minus F over F. Okay, so let's keep going with this. Let's cross multiply by F. So on the left side we have DI times F. And let's also cross multiply by DO. So on the other side we'll have DO times DI minus F. And if we distribute the DO into the parentheses on the right side, we have DI times F equals DO times DI minus F times DO. Okay, so the next thing we're going to do is we're going to take that equation and we're going to divide through on both sides by DI times DO times F. So here's what that looks like. So on the left side, we have DI times F. On the right side, we have DO times DI minus F times DO. But on both sides, we're going to divide through by DI, DO, F. So every single term is divided by DI times DO times F. All right? So in the first term, DI and F both cancel. In the second term, DO and DI both cancel. And in the third term, DO and F cancel. So this turns out to be much simpler. So here's what we got when we divided through. So to simplify this, we have 1 over DO on the left side, and then we have 1 over F minus 1 over DI on the right side, and we're basically done. We'll just write this in the standard form. 1 over F equals 1 over DO plus 1 over DI. This is what we call the thin lens equation. And basically, here's what you can do with it. If you know the focal length of your lens, and you know DO, in other words, you know how far from the lens you place the object, then you can figure out where the image forms. You can figure out DI. So here are the results. We have the thin lens equation, which says 1 over DO plus 1 over DI equals 1 over F. And also, we know something about lateral magnification that we didn't know before. The lateral magnification, which by definition is HI over HO, as we found, is also equal to the ratio di over do. But notice how we have a negative sign out here. Basically what that negative sign does for us is it tells us that our image is flipped upside down, it's inverted. So there are some sign conventions that are going to come along with these different variables. So let's explain some of that. The sign conventions for the thin lens equation. Okay, so let's start with the focal length, f. We're going to use a positive value whenever we have a converging lens and a negative value whenever we have a diverging lens. For the image height, hi, that's going to be positive if we have an upright image and negative if we have an inverted image. As for the image distance, di, that's going to be positive whenever we have a real image and negative whenever we have a virtual image. And then finally, the object distance, do. Let's think about this one. So there's a sign convention for do, which says if the object is on the same side of the lens as where the light is coming from, then do is positive. It's going to be negative if the object is on the opposite side of the lens as where the light is coming from. So that may sound a little strange. We'll sketch out what this means in a little more detail in a second. But basically, the only time do would ever be negative is if you're dealing with a system with multiple lenses. So if you just have a single lens, then do is always going to be positive, okay? Okay, so for a single lens, it's always going to be the case that do is positive. And to see why, let's just draw a picture of a single lens forming an image. So it doesn't matter what type of lens we have, but let's say it's converging for the picture we draw. Let's say there's a focal point here and here. Okay, so one of the rays goes parallel to the optical axis and then out through this focus. Another ray we could draw would go straight through the center of the lens like this. So you can see an image forming over here. So here's our object, here's our image. But notice that, okay, the object is on the left side of the lens, and the light is coming from the left side. In other words, these rays of light are originating from the left side of the lens. So our sign convention says if the light is coming from the same side of the lens as where the object is, then you have a positive do. That's always going to be the case if you have a single lens. It's only when we have multiple lenses where you can get do to be negative. And we're not quite ready to talk about multiple lens systems yet, so we'll see that when we get there. All right, so let's do an example. Let's say we have an object which is placed 85.5 centimeters from a converging lens, which has a focal length of 25 centimeters. Where is the image formed? I.e., what is the image distance? What is the lateral magnification of the image? Is the image real or is it virtual? Is the image upright or is it inverted? So here's what we're going to do. We're going to use the thin lens equation to make our calculations, to get all the numbers we need out. But then we're going to draw a ray diagram as a check. So we're going to verify that what we calculated makes sense by drawing the ray diagram. And if you do things right, your calculations should agree with the ray diagram. So that's what we're going to do here. Okay, so let's start by writing down what we know. do, which is the object distance, is 85.5 centimeters away from the lens. Also, the focal length of the lens is going to be positive 25.0 centimeters. Remember, f is positive for a converging lens. So if we use the thin lens equation, we have 1 over f equals 1 over dO plus 1 over di. So we'd like to solve for the image distance. So let's take 1 over di. That's 1 over f minus 1 over dO. So therefore di is going to be 1 over f 1 over f minus 1 over dO to the negative 1 power. So here's a mistake you don't want to make. This is not the same as just f minus dO. That is not correct. We actually have to do 1 over f minus 1 over dO, and then take that to the minus 1 power to actually get this right. So we have 1 over 25.0 centimeters here, minus 1 over 85.5 centimeters here, and then take that to the minus 1 power. So if you calculate this, you're going to get something positive, which is 35.33 centimeters. Keep 3 sig figs on that, 35.3 centimeters. Okay, so that's our image distance. Now notice we can immediately say something about what type of image we have. Because di came out positive, remember, this means we have a real image, according to the sign convention. Okay, now let's do the lateral magnification. M is equal to minus di over dO. So that's going to give us minus di, which we found is 35.33 centimeters, over dO, which is 85.5 centimeters. And so this comes out to minus 0.4132. Or to 3 sig figs, minus 0.413. Yeah. Okay, so notice how the magnification came out negative. This implies that we have an inverted image. So our image is going to be upside down, in other words. So this is what we've calculated. Now let's go to the ray diagram and see if this agrees with what we calculated. So first of all, when we make our ray diagram, we have to keep in mind that dO is greater than f. In other words, the object is outside of the focal length. So when we draw the object, we want it to be, again, outside of the focal length, so maybe somewhere over here would work. And let's start by drawing the first principal ray. Remember, the first principal ray goes parallel to the optical axis, and then it hits the lens. After going through the lens, goes out through the focus. So here is our first principal ray. Now the second principal ray goes through the focal point on this side of the lens, and then after going through the lens, goes out parallel to the optical axis. And then finally, so here, let's label that as number 2. And then finally, our third principal ray goes straight through the center of the lens without changing direction. So here's ray number 3. So we can very clearly see where the rays converge, which is over here. And if this is our object, our image is over here. And since we were following rays that originated at the tip of the arrow, this is where the image of the tip of the arrow must be forming. So in other words, we must have an inverted image. So think about what we just found. According to our diagram, okay, we have an inverted image. Okay, that's what we expected. It's also a real image because we actually have rays converging at a certain point where the image forms. And it's also smaller than the object, which is what we'd expect given that the magnification is less than 1. Okay? So this just shows that you can use a ray diagram to verify what you calculated using the thin lens equation. And so here's one for you to try out. We have an object placed 12.5 centimeters from a converging lens with a focal length of 25 centimeters. Same set of questions as before. Where is the image formed? So you're going to find the image distance di. What is the lateral magnification of the image? Is the image real or virtual? Is the image upright or inverted? And then draw a ray diagram to make sure that your calculations are making sense, okay? So pause the video, try to work this out, and then come back to it and we can go through it together. Okay, so what do we know in this case? We know that DO is equal to 12.5 centimeters. We know that F is 25 centimeters. Again, this is positive. We have a converging lens. And the thin lens equation says 1 over F equals 1 over DO plus 1 over DI. And we saw earlier that if we do a little bit of algebra and solve for DI, that's going to be equal to 1 over F minus 1 over DO to the minus 1 power. So in this case, we have 1 over 25 centimeters minus 1 over 12.5 centimeters taken to the minus 1 power. And so this will work out to minus 25.0 centimeters if you work it out. So that's our image distance. Now, since we have a negative image distance, the image is virtual. That's what this is telling us. And if we go ahead and calculate the lateral magnification M, which is minus DI over DO, so we have to be a bit careful with the signs here because if we have minus DI over DO, that's going to be negative 25 centimeters for DI over 12.5 centimeters for DO. So overall, this is coming out positive. Positive 2.00 is the lateral magnification. Now, since this came out positive, this is an upright image. And so that's what we can get from our calculations. So again, the next thing we want to do is verify that this all makes sense by drawing a ray diagram. So now this time, DO is less than F. So this is different from the previous example because the object is now inside of the focal length. So when we draw the object, we should show it in the focal length like this, closer to the lens than F. Okay, so this will be our object. So we'll draw 3 principal rays. Now the first one, as always, is going to go parallel to the optical axis. And then after exiting the lens, it's going to go out through this focus. So this will be principal ray number 1. Now our second principal ray starts going out through the focus. So here, we have to be a little careful with how we do this. So here's the focal length, or the focal point, f prime. We're going to draw a ray that goes through that focal point if we actually trace it back, so like this. And then after going through the lens, goes parallel to the optical axis. So that would be ray number 2. Okay? And then finally, ray number 3, as usual, just goes straight through the center of the lens without changing direction. So there's ray number 3. So notice something about these outgoing rays. Okay, the outgoing rays don't converge. So right away we should be thinking we probably have a virtual image. Now let's see what happens if we trace these outgoing rays behind the lens. Trace them backwards. So here, let's trace number 2 back behind the lens, like this. Let's trace number 1 back behind the lens like this. And then let's finally trace number 3 back behind the lens like this. Okay, so I obviously didn't draw this perfectly, but somewhere around here is where those rays would be converging if I drew this perfectly. And that means the tip of the arrow, the image of the tip of the arrow, is forming over here. So this is our image. So first of all, it's a virtual image because it's formed by the convergence of these virtual rays that we trace back behind the lens. It's also upright, and it's bigger than the object. Which perfectly agrees with what we calculated. Remember, we have a virtual image indicated by the negative image distance. We have an upright image indicated by the positive value of m. And also the magnification is 2. So that means the image is double the size of the object. So that's pretty much what our ray diagram is telling us. Okay, let's do another one. So here we have an object placed 85.5 centimeters from a diverging lens. So keep that in mind. We have a diverging lens now, which has a focal length of 25 centimeters. So same set of questions. Where is the image formed? What is the lateral magnification? Is the image real or virtual? Is the image upright or inverted? And then as always, we're going to use the thin lens equation to make these calculations, but then check the results using a ray diagram. So try to work this one out. Pause the video, see what you get, and then come back to it when you think you have your answer. Okay, so now we have DO. The object distance is 85.5 centimeters. And then we have a focal length F, which we need to put a negative sign on, so minus 25 centimeters, because F is negative for a diverging lens. Okay? So if we use the thin lens equation, 1 over F equals 1 over DO plus 1 over DI. And then we solve for DI as before. DI is 1 over F minus 1 over DO to the negative 1 power. Well, this is going to give us 1 over negative 25 centimeters, and then minus 1 over 85.5 centimeters to the minus 1 power. So, before we even calculate this, we can see the answer is going to come out negative because we just have 2 negative terms being added together. So this only can come out negative. And in this case, it comes out to minus 19.34 centimeters, or minus 19.3 centimeters to 3 sig figs. So one thing we immediately can see is that di is negative, which implies that we have a virtual image. And then if we go ahead and calculate the lateral magnification m, which is minus di over do, this comes out to minus negative 19.34 centimeters. That's di. And then do is 85.5 centimeters. This comes out to positive 0.2261, or to 3 sig figs, positive 0.226. Because m is positive, this means we have an upright image. Okay. So that's what we were able to determine by calculation. So now let's go to the ray diagram and then just verify that what we calculated makes sense. So DO in this case is greater than the focal length f. So even though f is negative, DO is greater than the absolute value of f, right? 85.5 is greater than 25. So what we have is the object outside of the focal length. So when we make the diagram, let's just make sure to put the object outside of the focal length. So here's the object. Okay, next we draw 3 principal rays. The first one goes parallel to the optical axis, and then it goes out through the focus, but remember this is a diverging lens. So this outgoing ray goes like this, it diverges, but if you trace it back behind the lens, it would go through this focal point here. So this is ray number 1. Okay, ray number 2. So the way we're going to draw this one is we're going to have it going towards this focal length on the other side of the lens. But then after going through the lens, it bends this way and goes parallel to the optical axis. Okay, so this is going to be ray number 2. And then finally, ray number 3, as always, simply goes through the center of the lens. Try that again, through the center of the lens without changing direction. Okay, so we can very clearly see that these outgoing rays are diverging. So they're not actually converging at any point, but if we trace them back behind the lens, so here we already have ray number 1 traced back behind the lens. Let's do the same for ray number 2. This outgoing ray, if we trace it back behind the lens, it's like this, and then ray number 3, if we trace it back behind the lens, is still right here. So this is the point where those virtual rays, again, that's what we get when we trace the outgoing rays back behind the lens. The virtual rays converge right here. And again, since we're following the rays going from the tip of the arrow, this should be the image of the tip of the arrow right here where the rays converge. So the image is upright, and it's virtual. And it's smaller than the image. Smaller than the object. So that perfectly agrees with what we found. We found a negative image distance, which indicates it's virtual. Found a positive magnification, which indicates it's upright, but the magnification was like 0.2, so it's a much smaller image than the object. And that's exactly what our ray diagram is telling us. So let's do one more. Now we have an object placed 12.5 centimeters from a diverging lens with a focal length of 25 centimeters. So same set of questions. Where is the image formed? What is the lateral magnification of the image? Is it real or virtual? Is it upright or inverted? Okay, so do the calculations with the thin lens equation and then draw the ray diagram to verify your results. So again, pause the video, try to work this one out, and then we'll go through it together. All right, so here we have DO equaling 12.5 centimeters, and the focal length is negative 25.0 centimeters because we have a diverging lens. The sign convention is to have F be negative. 1 over F equals 1 over DO plus 1 over DI, implying DI is 1 over F minus 1 over DO to the negative 1 power. So we have 1 over minus 25 centimeters, and then minus 1 over 12.5 centimeters, and then the negative 1 power. This works out to minus 8.33 repeating centimeters, which if we round it to 3 sig figs would be minus 8.33 centimeters. That's our image distance. DI is negative. That implies a virtual image. Okay, now for the lateral magnification M, which is minus DI over DO. This is going to be minus negative 8.33 repeating centimeters over DO, which is 12.5 centimeters. What does this work out to? Well, this is positive 0.66 repeating, which you can round to 0.667. And again, the fact this came out positive indicates an upright image. So let's do the ray diagram for this one. And we'll just remember that DO in this case is less than absolute value F. So the object is inside of the focal length. Which means when we draw the object, just make sure it's inside of the focal length, like this. So here's our object. So we'll draw the principal rays, starting with ray number 1, which goes parallel to the optical axis, goes into the lens, and then after going through the lens, it gets bent this way. And so if we want to know how it travels after going through the lens, we'll just remember it follows this line, which goes through the focal point, F prime. So this is our outgoing ray. This is number 1. Okay, if we draw ray number 2, this one starts off going towards this focal length, F. So let's draw that. Let's try that again. So it starts off going towards this focal point, F. But then after it goes through the lens, it gets bent and it goes parallel to the optical axis. So this is ray number 2. And if we take ray number 2 and we trace it back behind the lens, this is what we get. So by the way, we call these dashed lines the virtual rays. And then finally, let's do ray number 3. It goes straight through the center of the lens, and it's not bent after going through the lens. So there's ray number 3. So notice how the outgoing rays, once again, diverge. So there's no real image forming. It's only that when you trace those outgoing rays back behind the lens, they appear to converge right here, which is where the image of the tip of the arrow is forming. So here's the object, here's the image. They're kind of close to each other now. But we can notice a few things about the image. It's certainly virtual. That's exactly in agreement with what we calculated. It's also upright. And it's also smaller than the object. So again, the ray diagram verifies what we calculated. Okay, so let's take a second to summarize everything we found in the last 4 example problems. So in particular, what kind of images are formed when you have a single lens? So there are 3 possible cases. The first case is where we have a converging lens and the object is outside of the focal length. So DO is greater than F. So that's shown in this diagram here. We have the object outside of the focal length. And if we draw the 3 principal rays, we see that a real image forms on the opposite side of the lens, but it's inverted. So the arrow is upside down. Case number 2 is we have a converging lens and the object is inside of the focal length. So DO is less than F. So that's this situation here. We have the object inside of the focal length. If you draw the 3 principal rays, as we did, you'll see that the outgoing rays don't actually converge, which means we have a virtual image. If you trace those outgoing rays back behind the lens, you see a virtual image forms over here, and that virtual image is upright. And then finally, the third case is where we have a diverging lens. So when it comes to a single diverging lens, it doesn't matter if we put the object inside the focal length or outside the focal length, it's always going to come out the same way. You're going to get a virtual and upright image. So with a diverging lens, regardless of where you put the object, you draw your 3 principal rays, and you see that a virtual image forms on the same side of the lens as the object, and it's upright. So that's just a summary of the different examples we did. Okay, so I have another example for you guys to think about here. So the first question is, if an object is placed at the focal point of a converging lens, what is the image distance going to be? So try to use the thin lens equation to figure that one out. And then as a follow-up, if the object is placed infinitely far away from the lens, what will the image distance be in that case? So pause the video, try to figure this out, and then we'll go through it together. Okay, so we'll start with this. We have an object at the focal point of a converging lens. Okay, so first of all, this means F is positive because we have a converging lens, and DO is going to be equal to F if we place it right on the focal point. So using the thin lens equation, 1 over F equals 1 over DO plus 1 over DI. Essentially what we're doing here is we're saying 1 over F equals 1 over DO, which is the same thing as F, so we have 1 over F again, plus 1 over DI. Okay, so we put DO equal to the focal length, which means these two terms cancel, and then we have 1 over DI, is equal to 0. Okay, so let's really think carefully about this. If 1 over di is equal to 0, that means di can be, of course, infinity, but also minus infinity works too. Plus or minus infinity is really the answer here. So let me show you why that is in a few different ways. So first of all, if we have the function 1 over x that we're plotting versus x, the shape of this curve is this. Okay, so it behaves differently when x is positive versus when it's negative. Okay, and as 1 over x approaches 0, that's what we're looking at here, 1 over x going to 0. Well, basically, that's happening over here. You see 1 over x is going to 0 in the region where x is going to infinity. But that's also happening over here. 1 over x is going to 0 in the region where x is going to minus infinity. So the point is, if 1 over di equals 0, that means di could be positive or negative infinity. So let's try to make sense of that using a ray diagram. Okay, we have the optical axis. We have a converging lens. And then we have a focal point here and here. And we have the object right at the focal point. So if we draw some of the principal rays, like this one, for instance, going parallel to the optical axis and then out through the focus like this. And then let's draw another one. How about the one that goes just straight through the center of the lens like this? So actually, these two outgoing rays are parallel, so they're never going to converge. So they never converge, which means the image distance is all the way out to infinity. On the other hand, if you trace the virtual rays back behind the lens like this, those virtual rays are also parallel. Meaning they never converge, meaning we can also consider the image distance to be minus infinity on the other side of the lens. Okay, so that's how we make sense of plus or minus infinity. Okay, lastly, let's look at the second question, which is we have an object placed infinitely far away from a converging lens. Okay, so in other words, DO is now going to infinity. So if we have 1 over f equaling 1 over DO plus 1 over DI, we have 1 over f equals 1 over infinity plus 1 over DI. 1 over infinity goes to 0. 1 over f equals 1 over DI, which means DI is equal to f. So the image now forms at the focal point. So if your object is infinitely far away, the image will form at the focal point. And to make sense of this, we can again draw a ray diagram. Now, it's hard to actually draw the object infinitely far away, so I'll just draw it very far away from the focal point. So here's the optical axis. Here's our lens. And let's say the focal point is here, and there's another focal point here on the other side of the lens. And again, we just want to show the object being very far away. So the object is way out here. In other words, DO is a lot bigger than F. So we can draw a couple principal rays. Once again, we have a ray that goes parallel to the optical axis all the way to where the lens is located. And then it goes out through the focus. And let's just draw one more of those rays. How about the one that goes straight through the center of the lens? Like this. Now you can see the image is forming over here. It's not exactly at the focal point. It's very close to it. But of course, in the limit where DO actually goes to infinity, DI is going to be exactly going towards F. Okay, so that's the idea here. And we'll end this video here. We'll pick back up in the next one. So until then, take care, be safe, be healthy out there. See you later.